Welcome to Unit 8, Inference for Categorical Data, chi-squared. In this video, we're going to cover topic 8.3, carrying out a chi-squared test for goodness of fit. Hopefully you've watched topic 8.2 already, which covers steps 1 and 2 of the process for a chi-squared goodness of fit test. And in this video, we're going to talk about steps 3 and steps 4. All right, so now that we know really what a goodness of fit test is, when it's needed and how to recognize it, and how to set it up, we can move on to actually using statistics to make a decision about the question being posed. So this is very similar to us, in step 3 of our previous test with proportions or means was to find the test statistic, right? To get that Z-score or T-score. And that Z-score is super important because it tells us, it's a measurement of how far our sample value is from the mean. And if we're really, really far, then that means our sample is really, really significant, which alerts us that, whoa, maybe that does give us evidence that that mean that we thought was in the middle is actually wrong and that the alternative should be taken. So it's a very similar process, but we don't have a T-score and a Z-score. We have what's called a chi-squared score. And now remember, chi-squared, a lot of people just see the writing of it, C-H-I squared, but it's actually a Greek letter, as I talked about before, and it's kind of like an X little curve there, chi-squared. So we're not going to find a T-score or Z-score, we're going to find a chi-squared score. So let's quickly review the example that we started in last topic, 8.2, to kind of see where we're headed with this. All right, so this is the example of eye color. Now remember, we took a random sample of 450 people in Ohio, and the results showed the following distributions of eye color: blue, brown, green, hazel, amber. But we've known nationwide the proportion of eye colors has typically followed this distribution: 10%, 78%, 2, 5, and 5%. And the question was, is there convincing evidence from our sample that Ohio is no longer the same distribution as the rest of the nation? Is the nationwide proportions that we've always believed to be true no longer valid for Ohio? Is Ohio something different, right? So basically we're saying, hey, how good does the data from Ohio fit with what we expected? So step 1, of course, was creating the naming it. It's the chi-squared test for goodness of fit to see if the distribution of eye color is different than what was expected. The null and the alternative, again, I highly recommend writing this out. The null is that the distribution of eye colors of Ohio are consistent with what was expected from the researchers' claim. So the null is that, nope, Ohio is no different than the rest of the nation. And the alternative is literally the exact same sentence, just putting the word not in there, saying that the distribution of eye colors for Ohio are not consistent with what the researchers claimed for the nation. Now, you could use numbers and symbols here, but this is kind of long and honestly, I think more complicated to write out. I don't actually like that, but it is acceptable. So then we moved on to checking the conditions, which are pretty basic. We should be familiar with them. It's got to be a random sample to avoid bias. Got to be under 10% of all adults in Ohio to assume independence. And we do need 5 or more expected values in each category, which then allows us to move on to actually creating the expected counts. And that's, of course, using the percentages. And we did this all back in 8.2. So the observed values were the 40, the 370, the 5, the 20, the 15 that we actually saw in our data. And the expected counts are based on the proportions or the percentages that were given to us from the typical nationwide data. So if you're not quite sure where I got these expected values from, you might want to go back and watch the 8.2 video. All right, so now comes time for step 3. And this is where we're actually going to find that chi-squared statistic and p-value that I was talking about earlier. So no z-scores and t-scores here, but this is in a lot of ways similar to that, right? Because remember, in a proportion test or a mean test, the next step is to find the z-score, the test statistic that tells us how many standard deviations our particular sample is away from the mean of all samples. So this is a little bit different, but it's called chi-squared. Again, there's that little X squared type symbol here. Now what this measures, it doesn't measure how many standard deviations you are from the mean. It measures the distance between observed and expected counts relative to the expected counts. So you'll notice in the numerator, we just take the observed value minus the expected value. So what we saw was blue eyes minus what we expected was blue eyes, and we square that number, and then we divide by the expected count, and that keeps it all relative to the expected counts. Now this symbol right here is the summation symbol. So basically we have to do this formula. We have to apply this formula to every single category. Blue eyes, green eyes, hazel, brown eyes, and so forth. And then we add them all together because that's the universal symbol for sum, or add them all together. So we got to add up all those values. So notice that chi-square distributions always have positive values. That's because we're squaring, right? Anytime you square a difference, yeah, a difference could be negative or positive, but when you square it, it always becomes positive. And that creates a model that's skewed right. So notice that when we work with z-scores and t-scores, we use an approximately normal distribution where we see a tail to the left, a tail to the right, and we talk about most data is in the middle, and some very rarely is really low, and some data very rarely is very high. Well, with chi-squared, it's a skewed right distribution, right? And this model is simply showing us all possible values of chi-squared that are out there. Just like a normal model shows all possible z-scores that are out there. Most z-scores are really, really close to the mean in the middle, and some z-scores could be unusually high, but that obviously becomes more and more rare and significant. So this is a very, very similar, right? So this model, this distribution that we're seeing down here that's skewed right, it's filled with chi-squared scores. And basically we're looking for where is our chi-squared. You know, if our chi-squared scores right in here, well then guess what? It's not significant. It's pretty much, in a sense, normal, right? It's just like all other chi-squareds. But the further and the further your chi-squared value gets to the right of the tail, the more unlikely and significant it becomes. And again, just like we saw that with z-scores and t-scores, you know, when you get a z-score of 5.5, you're like, oh my gosh, that's a really high z-score. I'm probably going to reject the null because that shouldn't happen. And when a z-score that big does happen, that gives us evidence that, you know, the alternative is true. That's the exact same thing here. Now, there is a degrees of freedom. There is not one and only one chi-squared model. So it's almost like t-scores in the sense that there's different ones, right? In fact, the skew actually becomes less pronounced with increasing degrees of freedom. Now, the degrees of freedom here is a little bit different than we've ever seen in the past. So you got to do a little bit of studying to remember this. It's not the sample size -1. It's the number of categories -1. So if you have 5 different eye colors, 5 -1 would be 4 degrees of freedom. So it's the number of categories -1, not the sample size. So a very common mistake there. So, you know, to kind of sum this up, this is the number we need. Just like a z-score or a t-score can kind of really give us a good idea of where our sample falls in the data. Well, that's exactly what a chi-squared does. It really kind of tells us where do our observed values fit within what was expected, okay? And we're going to demonstrate, of course, several times in this video how to actually find that value, okay? But once we have that chi-squared, kind of just like a z-score, t-squared, of course, we need to actually go ahead and get our p-value. So using your observed and expected counts, find the component chi-squared value. Now the component chi-squared is each individual. So you're going to actually go to each category and do observed minus expected squared divided by expected. And I'm going to walk you through all this in a moment. So we call those the component chi-squareds because you're going to find each of the individual chi-squareds for each category, and then you add them all together to get the total chi-squared value. Once you have this total chi-squared value, you then need the p-value. And to get that p-value, we don't use normal CDF because we're not working with z-scores. We don't use t-CDF. We're not working with t-scores. We're going to use, on our TI-84 calculators, chi-squared CDF. And chi-squared CDF only goes to the right. You never go below. So you're always going to start at your chi-squared value. That's the chi-squared value that you got in your data. You're going to go towards infinity, which we're going to just use 99, way, way above. And then we have to have that extra comma for the degrees of freedom. That way it's specifying the actual individual model that we're going to use. Now, let's make sure that we remember what a p-value is, right? Interpretation of the p-value, it's the probability, given the null hypothesis is true, of obtaining a test statistic equal to or greater than the observed value. So the p-value is basically saying, hey, what's the probability of seeing what we observed or greater or even higher than what we observed, assuming the null is true. So very similar to how we interpreted a p-value before with z-scores and t-scores, okay? Now we are going to need the TI-84 calculator, and where do you get chi-squared CDF? It's in the same location you get normal CDF and t-CDF. All you gotta do is scroll down a little bit. And we will walk you through all of that in this next example. That way you can actually see how it works. I'll even show you on the calculator. All right, so let's move on to step 3 for that eye color problem, right? So now that we have our observed counts that we found back in, actually where they're given to you, and then we found the expected counts, which we did back in step 2, now we got to find the component chi-squareds. So you'll notice exactly what I did here, and I made the math crystal clear so you could see it. We took the observed value, which for blue was 40, minus the expected value, which for blue was 45. We squared that, and we divided by the expected 45. Let me just quickly show you how to do that in the calculator. Use parentheses. It's a time saver, right, for sure. So we have 40 minus 45. Close those parentheses. Square that. Divide that by 45. So observed minus expected squared divided by the expected. And that's how I got the 0.556. And then you're literally just going to repeat this process for every single category to get all of your component chi-squareds. So you're going to do the brown. 370 observed minus 351 expected squared divided by 351 expected, and I get 1.028. So remember, chi-squared is a measurement of how far your expected values are from your observed values relative to the expected. So the higher the number that you get for chi-squared, the further away that your data must have been from what was expected. So for example, blue, 40 and 45 are pretty close, so notice it's a little bit of a lower chi-squared. Whereas if you go to amber, 15 and 22.5 is a little bit further away. It's a little bit bigger chi-squared there, but it's all relative to what was expected, okay? So then we get the total chi-squared literally simply by adding them up. And again, that's what that sum symbol stands for right there. That symbol we see in front of the chi-squared formula is to just add them all together. So we add up all of those chi-squareds, which does take a little bit of time. So this is a little bit of the time-consuming part of this problem, but we get 6.14. So now the question becomes, is that high? Now, if this was a Z-score, we'd be like, oh my gosh, 6.14, that's really, really high. But remember, this is skewed right, so we don't go to the left of 0 at all. So 6.14, I don't know, might be high, might not be high. So we really can't make a quick, objective guess or anything like that based on chi-squared. I've mentioned in past videos, when you get that Z-score, you probably kind of already have a feeling for how things are going to work out for your conclusion. Not necessarily true with chi-squared, just because it's newer to us. All right, so now we need that p-value. We do need our degrees of freedom. So you'll notice I have 1, 2, 3, 4, 5 categories. 5 minus 1 is 4 degrees of freedom. So we're going to go to chi-squared CDF on our calculator. So that's under second vars, just where we get normal CDF, TCDF. Notice number 7 is chi-squared PDF, just like we never use normal PDF or TPDF, we'll never use chi-squared PDF. And number 8 there is the chi-squared CDF. So the lower value, because there's no negatives, the lower value is always whatever your observed chi-squared was, which was for us 6.14. And I'm going to go really high. Now remember, this is skewed right, so we only go to the right. So I'm actually going to go to 999. I really don't need to do that. I'm just kind of being exaggerating there. But I'm just exaggerating the fact that when you're skewed right, we got to go way, way, way to the right. So I'm using 999 basically as my infinity. And then again, I need 4 in there for the 4 degrees of freedom. And this is going to get you the p-value 0.1889 that we would get. So basically, remember, chi-squared is going to, your chi-squared, 6.14, is going to fall somewhere on this model. So for example, here it is right here. And then the p-value is the probability that we are above that. We are more than that. So this is the p-value, which is what the chi-squared does for us. So it's the probability that a chi-squared value comes greater than 6.14. Okay, so pretty simple process there. Now, step 4 is, of course, making the conclusion, which we should be really good at by now because this is literally the exact same it's been for the last 2 units. If the p-value is below the level of significance, we will reject the null hypothesis and say that we have significant evidence that the alternative is true. Of course, we got to put some context in that. Now, remember, the level of significance is alpha, and typically we go with 1 or 5%. If a problem does not tell you, then you get a pick, whatever you want, 1 or 5%. If a p-value is above the level of significance, we fail to reject the null hypothesis, and we say that we do not have significant evidence that the alternative hypothesis is true. So we love p-values that are really, really small, like 0.000001, because those are clearly going to tell us to reject the null. That's way below any level of significance. That means our data is very significant, hence reject the null, go with the alternative. Now, I'm not going to say we love p-values, but p-values that are really high, like 0.3, 5, 6, 7, p-values are going to be way above any level of significance we choose. obviously that means that our data is just, well, likely. It's not weird. It's likely if the null is true. It's not unusual data, which means we failed to reject the null. You know, p-values that are of concern to us are something like maybe 0.03, right? Because if you use 1% significance, then this is greater, so you would fail to reject. But if you use 5% significance, then this would actually be significant and would cause us to reject the null. So, you know, if you're not told the level of significance, you are allowed to pick, but be careful because that decision could be crucial depending on what your actual level of significance is. But at the end of the day, you do what you do based on the level of significance you have. All right, so here's my well-written conclusion based on this. So since the p-value of 0.1889 is greater than 0.05, I will fail to reject the null hypothesis. There is no significant evidence that the distribution of eye colors for Ohio adults is not consistent with what was expected from the researchers' claims for the nation. So yes, we did see a distribution that was not exactly matching up with what we expected, but it wasn't so far off that we could claim Ohio is crazy and different than every other state in the nation in terms of eye color, okay? So the distribution of eye colors for adults in Ohio is not significantly different than the distribution of the nation as a whole. So when we fail to reject the null, we just don't have evidence to say that Ohio is significantly different than everybody else. The eyes of Ohio are probably no different than the eyes of the nation. We did see some slight differences, but nothing too significant. Now remember, when you do have that high p-value, what you're basically saying is, hey, listen, yeah, I didn't necessarily see what I thought I was going to see, but you know what? That's what happens when you sample. Sometimes random samples don't match up perfectly. It doesn't necessarily mean anything. And that's what ended up happening in this problem. All right, so I really encourage you to go back and walk through each of these steps if you want to kind of see how it's all done. But I am going to go through one more example that we started back in 8.2 as well. And this is the deer problem. Where do deer live? So just to give you a quick recount of this problem, if you don't remember, basically we were wondering, researchers have always believed that the proportion of deer that live in a habitat is equal to the proportion of the size of that habitat. So for example, if habitat 1 has 10.5% of the forest is habitat 1, then you would expect 10.5% of deer to live there. Vice versa, maybe habitat 4 has 26.3% of the forest is in habitat 4, so we would expect 26.3% of the deer to live there. Well, we want to know, you know, some researchers think that no, that's no longer true and that deer actually prefer certain habitats regardless of the size. So we have 4 habitats, we got what the proportion of the forest that those habitats represent, and we got the number of deer that we counted in a sample that live in each of these habitats. And they do want us to see if there's convincing evidence that the number of deer living in each habitat is not proportional to the size, and they do want us to use the 5% levels. They are giving us our significance level. All right, so the null hypothesis was that the distribution of deer living in the specific habitat of a forest is proportional to the size of the habitat. So the null is what scientists have always believed, again, that the number of deer is equal to the proportion of the size of the habitat. And the alternative is literally just throwing that word not in there, saying that the distribution of deer that live in a specific habitat of a forest is not proportional to the size of the habitat. All right, so step 2 is checking those 3 very basic conditions and actually getting the expected counts. So once again, the observed counts are going to be given to you in the table. So I just added this new column here, which they love on the AP test when you make a little, kind of like, you know, organizing your work. So again, where did I get these expected numbers from? Well, again, that was based on the proportion size of the habitat, because the null says that the number of deer should be equal to the proportion of the habitat. So again, if that is true, because I have to assume the null is true, if 10.5% of the forest is habitat 1, proportion 0.105, then that of the 350 deer in my sample, that's the proportion that should be living there, which is 36.75. So it's just some quick multiplication. Again, habitat 2 was 35.4% of the forest, so 35.4% of the deer, 123.9, should be living there. Same thing for habitat 3 and habitat 4. All right, so now we're going to move on to the new stuff, right? Step 3 is really getting those chi-squared values and that p-value. So here it goes. Notice that I have to do it for each habitat. So habitat 1, 2, 3, and 4. Observed, 44, minus expected, 36.75 squared, divided by 36.75. Please be very, very careful, especially typing this into the calculator. Be diligent, take your time. So I'll do the next one here, 124 minus 123.9. Oh my gosh, look how close that was. We observed 124, we expected 133.9. Oh boy, that's close. Almost exactly right. Squared divided by the expected number. And because that was so close, look how small that p-value, or that, excuse me, not p-value, that chi-squared value was. I actually just wrote down 0.00 because, I mean, it's 0.0000807. It's so tiny that it's really insignificant at that point because it was so close. But notice things take a drastic change. Habitat 3, 35 expected, 97.3. 35 observed, 97.3 expected. Whoa, way far off, which produces a very big chi-squared component. So Habitat 1 was pretty close. Habitat 2 was really close. Habitat 3 and 4 seem to be way off. And again, remember, it only takes one category to be off for all of the data to be, well, inconsistent. So let's finish up here. So I'm going to add all of those chi-squareds together, and that's where I get the total chi-squared, 74.12. So then I'm going to go to chi-squared CDF on my calculator. And it takes a little bit of time to scroll through on that list there. Oh, sorry, I went way past it. Number 8 there. If you remember what number it is, you can just hit the numbers a little bit faster. And this time I'm going to go from 74.12 to 99 degrees of freedom. Well, there's 4 categories, habitat 1, 2, 3, and 4. 4 minus 1 is 3 degrees of freedom. And I get an unbelievably low, right? 15 zeros. I count them. I hope that they're all there. I'm not sure if they are. 0.00000000559, right? I don't know. You can count all my zeros to see if I got them all there, but 15 zeros there should be. That's really, really low. Now think about that. Remember that chi-squared, right? That chi-squared. Now we're not as familiar with chi-squared models. We are with Z's, normal models and so forth, but a 74.12, that's going to be way over here somewhere. That's going to be an unbelievably high chi-squared number, which puts a very, very, very small proportion of data above it. So no wonder our p-value is so small. Now what this tells us is that, what we saw, the observations that we saw in the forest are very, very, very rare if the null is true. So if the null was true, that the deer was proportional to the size of the habitat, we should not be seeing the numbers, right? These numbers should not be occurring because look at the probability of these numbers occurring, extremely unlikely. But since they did occur, that's what gives us the conclusion we want. So since my p-value is so far below 0.05, I will reject the null hypothesis. There is significant evidence, a lot of it, that the distribution of deer that live in a specific habitat of a forest is not proportional to the size of the habitat. If you go back and look at the numbers, deer clearly favor habitat 4, with many more deer living there than was expected. Something about habitat 4 must be desirable to the deer. Maybe there's a good source of food there or a stream with fresh water. The deer also seem to dislike habitat 3 with far fewer deer living there than expected. Maybe habitat 3 just had a big fire and there's, not anywhere nice to live, no place to take cover. There's a big forest fire there. Who knows? But if you actually go back and look at the data, you could actually see that habitat 4 had way more deer living there than were expected. Habitat 3 had way less than expected. And sometimes there might be a follow-up question on the AP test about, what category really made the deciding factor for you? And I would say probably here's a toss-up between 3 and 4. You can actually look at the chi-squared components to see that. Habitat 3 was 39, Habitat 4 was 32. Those are huge chi-squared numbers. They're going to really make the decision for us. Whereas again, if you look at Habitat 1 and 2, like if we only looked at Habitat 1 and 2, we'd probably be failing to reject it all. I mean, the numbers are really close. But because of Habitat 3 and 4, boy, oh boy, it certainly does not appear that the deer that live in each habitat are proportional to that size of the habitat. There's something going on where deer favor habitat 4. And again, I'm talking about this right now because this is the beauty of stats, right? Once you understand all the number crunching behind it, the conclusions where you could actually kind of talk and breathe and discuss what you're learning from this problem. And you could start to ask questions like, why? Why are deer going to habitat 4? Why are they not going to habitat 3 and so forth? Because that's the important part of statistics is they allow us to really start to recognize what's happening in data and then actually talk about it, make decisions on it. And maybe we could do something like if habitat 3 is undesirable, maybe researchers could do something to make it desirable for deer, plant trees there, give a food source there, something, You know what I mean? Okay, so I'm rambling on now. Sorry about that. But hopefully you now understand the full process for a chi-squared test for goodness of fit. They're actually quite easy and fun. Fun, I think, yes. The most time-consuming part is actually sitting and doing all the chi-squared calculations, but it's well worth it if you just sit and do it. It's not too bad. No problem is going to give you a data with 13 categories where you're just doing all these calculations. That'd be pretty mean. So overall, not too bad. All right, guys, that's it. Hope you understand it. Hope you learned it. Watch it again if you need to.